Hello teachers, today we want to talk about section 13-3, the Pythagorean Theorem. That includes the distance formula and the equation of a circle. At the moment it might not seem like they have anything to do with each other, but they have everything to do with each other. At the end of this section you should be able to explain and understand the Pythagorean Theorem and its converse, measures of sides in special triangles, the distance formula, and the equation of a circle. So we're going to start off talking about parts of a right triangle. Now notice this is very important. This entire discussion is in regards to a right triangle. So notice we have the right angle here at the bottom, the side directly across from the right angle, so always directly across from the right angle is called the hypotenuse. We typically label that C. And when we use the Pythagorean Theorem, which is coming up in just a second, that's always the C value. And then you have legs, A and B. And you typically don't have to distinguish between these legs. So it wouldn't matter if this side was A or B, or if this side was A or B. And what I'm talking about is using the Pythagorean Theorem. So given a right triangle with legs A and B, and hypotenuse C, then the relationship between these sides is always C squared is equal to A squared plus B squared. And I tend to say it the other way, that A squared plus B squared equals C squared. So again, very important that this C squared, the one it's equal to, is always the hypotenuse value. Also, don't forget to square each of the sides when you use it. So for our first problem here, they tell us that BC is 3 centimeters. And I'm just going to draw it on the picture. So BC, notice that is the line segment at the bottom of the triangle, is 3 centimeters. And that AC, so notice AC is the leg, vertical, is going to be 4 centimeters. What is the length of AB, which happens to be the hypotenuse? So we're trying to find C. So if I use the formula A squared plus B squared is equal to C squared, again I encourage you to write it down every time you use it, then A squared is going to be 3, and I'm going to leave off the centimeters. Okay, now you could include it in there, that would be 3 centimeters squared. And we'll talk about that, but it's really not required. You're finding a length, so it's also going to be in centimeters. Plus B squared, notice we have the other leg, which is 4 squared, equals C squared. Parentheses not required when you're dealing with positive values when you square them. 3 squared is 9, plus 4 squared is 16. Make sure you square each first. Equals C squared. That gives me that 25 is equal to C squared. And then when I take the square root of 25, I'm going to get 5. Now typically when you take the square root of both sides of an equation so that you can eliminate the square, you're required to put a plus or minus in front of one of the sides. But we are not required to have the minus answer. Why do you think? Well, we're talking about distance, right? So the negative answer doesn't make sense in this particular application. The side lengths of a triangle are always going to be positive, and there we go. So the hypotenuse in this particular situation is 5 centimeters. And if you think about the math, had you plugged in units, that would be centimeters squared plus centimeters squared. And then over here, when we take the square root of centimeters squared, that would give us centimeters back. Just, you can leave it off and just add it back later. And there, of course, is our typed up version of the answer. That's the 5 centimeters that we got. So we have another problem right here. I think it's worth pausing the video and you calculating this on your own and see how it goes. So how did it go? You feel comfortable? It says the size of a rectangular television screen is given as the length of the diagonal of the screen. Okay, so we're talking about this length right here, and when you buy TVs, that is the case. If the length of the screen is 24 inches, so we know if this is 24 inches, and the width is 18 inches, notice, oh, they said the length is 24 inches. I'm not paying attention, and it's already labeled for us. Okay, and the width is 18 inches. What is the diagonal? Now, if you buy a TV, you're actually going to know the diagonal, and that's why I'm not paying attention, put it over at the diagonal area. So they would sell the TV using the value we're about to calculate. So you've got 18 squared plus 24 squared. Now, what if I had put 24 squared plus 18 squared? Is that okay? Sure it is. The order that you put the legs into this formula doesn't matter. And we're doing a squared plus b squared is equal to c squared. Is once again the hypotenuse is the value that we are trying to find. Okay, and then you might want to use your calculator or multiply these out by hand. That's up to you. 18 squared is 324 plus 24 squared is equal to 576. That's equal to c squared, and then do add those, and that gives me 900 is equal to c squared. And what's the square root of 900? Well, you know that's 30, right? And that gives me c is equal to 30. Go back and check your units. Remember, we were talking inches. This was inches and inches, therefore our diagonal is 30 inches. So this would be sold as a 30-inch TV. And if we look up the typed up version of this result, there it is, real simple. 18 squared plus 24 squared is 900, and that gives us 30 when we take the square root of both sides. How about the next example? It says a pole BD is 28 feet high. So, and it's got it labeled for us. There's our pole right there. Okay, it's perpendicular to the ground, so that's why the right triangle notation. Two wires BC and BA, look like guy wires, each 35 feet long, notice that's labeled for us as well, are attached to the top of the pole and to stakes A and C on the ground. If points A, D, and C are collinear, remember what that means. They all lie on the same line. So A, D, and C all lie on the same line. How far are the stakes A and C from each other? So what could we do here? If you know what to do, definitely pause it and go ahead and calculate and see how it goes. But what could we do here? Well, let's focus only on the right triangle, right? And there's two of them. So I'm going to look at the one to the right here. And it wouldn't matter if you looked at the one to the left. Now, what information do we have? So we have a leg, which is 28 feet. And then I have a base down here, line segment DC, that I'm trying to calculate. And then my hypotenuse is 35 feet. So when I use the formula a squared plus b squared equals c squared, I have an A or a B. It depends on what you want to do. I'm going to say 28 feet is my A. So 28 squared plus b squared is equal to my hypotenuse is over here at 35 squared. Now let's do the math real quick. So 28 squared. I'm trying to do it real quick and I'm not doing it real quick. Is 784 plus b squared is equal to 35 squared is 1,225. Now I've got to solve for b squared. So what am I going to do? Well, I'm going to use my property of equality and subtract 784 from both sides. That's the addition property of equality. We're really adding a negative 784 to both sides of this equation. So that gives me b squared is equal to 1,225 minus 784 is 441. And then I use my square root property and calculate the square root of 441. And that gives me the result that b is equal to 21. Okay, now we're talking feet, right? Go back and look at your units. That's 21 feet. But keep in mind, that is only the distance from D to C. Now you could argue that this would also be 21 feet from A to D because these are symmetric triangles here. Okay, and then 21 feet plus 21 feet is 42 feet. And then go back and make sure we really did answer the question. How far are the stakes A and C from each other? Definitely 42 feet. And if I go look at the typed up version of that, I have another blank screen. There we go. There's that 42 feet we were looking for. And so notice they did the same work that we did. They called that distance, that leg, DC instead of B. You can call it whatever you like as long as you can keep up with your variables. All right, here's another one. I think you should try this one on your own. It's an interesting problem. It says, how tall is the Great Pyramid of Cheops? A right regular square pyramid. So notice we do have a square base. That's what they mean by right regular square pyramid. And then the altitude that comes from the point E straight down is perpendicular. So that's why the right angle here. Okay. All right. If the base has a side of 771 feet, okay, so down here at the bottom is 771 feet, and the slant height, or the altitude of EAB, okay, is 620 feet. Notice they've got an arrow there where that's labeled. Now, notice the triangle you're working with here. I'm going to highlight it in green. There is your right triangle right there, okay? You go ahead and pause it and calculate. Now, once again, we are allowed to use the Pythagorean theorem, but why? Well, you would argue there is a right triangle, and let's be clear about what we're looking for. Okay, now we know we have a distance of 771 feet as the side of the pyramid, okay? A regular base has a side of 771 feet. That's not our leg value. Right? That's just the side of the pyramid. So what would the leg value, or FD, the line segment FD, what would that value be? Well, again, it says that it is a regular square pyramid. And because this is a regular square down here, this altitude is going to come down and hit the center of the square. Therefore, the length of FD is half of the side of the pyramid. So we need to take 771 and divide it by 2, and that's going to give me 385.5. So FD is 385.5. Is that enough information to get this done? Sure. Let's let 385.5 be our A value. Our B value is actually the height. That's what we're looking for. I'm just going to call it H squared for convenience. And our hypotenuse is the slant height. That's 620 feet. Don't forget to square each of those. And so when I calculate this, when I get the H squared by itself, what I'm really going to be typing in my calculator is H squared is equal to 620 squared minus 385.5 squared. And that's going to give me 235,789.5. And then I want to take the square root of that value. And remember, again, algebraically, if you use the square root as a tool in your algebra problem, you're supposed to put plus or minus. But the minus doesn't work for this application because the length of a triangle cannot be a negative number. So I'm leaving off the minus in this case. So I'm going to take the square root of that answer, and I get 485.58. Now, remember, I took that 771 feet and divided it in half, and that gave me 385.5. I really don't want to take it out any further than that, so let's just say 485.6 feet would be the height of our pyramid. In fact, they might have just written that as 486. Let's find out how this went. Okay, they wrote it as 485.6. Notice the steps are the same. They said that DF is half of AB. Okay, so let's find DF. We talked about that. Is half of AB, which is also 771 feet. Okay, and that gave us the 385, and then you plug that into the Pythagorean theorem, so I think you're okay. We probably don't have to go into that in detail. Next, let's talk about special right triangles. There are two right triangles that are really worth memorizing the side lengths and the ratio of one side compared to another. So I want to first look at the left triangle. All right, so notice the details here. We know that this angle is 45 degrees and this angle is 45 degrees. Now we know what that means. If your base angles are the same, then we know we have an isosceles triangle. So that means this side length is going to match this side length. And so just selected, let's decide that this length is going to be 1 to keep things simple, which means this side is going to be 1 as well. Well, if we use the Pythagorean Theorem, we know that 1 squared plus 1 squared, well, I square each of those. That's 1 plus 1 is 2, and that's going to equal c squared, and then I take the square root of both sides, and that's where the square root of 2 comes from. Okay? Well, for any side length, not just for one, but for any side length, as long as you have a 45, 45, 90, and notice that's the way it's named up here, a 45, 45, 90 degree triangle, then no matter what these side lengths are, the relationship to the hypotenuse is going to be s square root of 2. So if these were side lengths of 3, then the hypotenuse would be 3 square root of 2. Or if these were side lengths of 111, then it would be 111 square root of 2. And that's worth recognizing. So if you have a triangle where, again, 45, 45, 90, and if you know a side length, then you automatically know the hypotenuse. So next I want to talk about relationships of sides in a 30, 60, 90 triangle. Okay, so that means you have a 30 degree angle, a 60 degree angle, and a 90 degree. Now notice everything in this section has a 90 degree because we're talking Pythagorean theorem, and that only applies to 90 degree or right triangles. But look how we started. The figure on the left, we have a triangle. Notice it's an equilateral triangle. So each side length of the entire triangle here is 2. Side length 2, side length 2, side length 2. Now why did they pick 2? Well, I'm going to tell you. Because we divide it in half by pulling an altitude straight down. Notice that's my 90 degree angle, because originally the equilateral triangle doesn't have a 90 degree angle. But if you draw an altitude here, there's your 90 degree angle. So the triangle that we're really taking a look at here is this one. Now when I take that length of 2 and cut it in half, that's that base of 1 that we like to mention. Just super basic 1 here. Okay, well if this is 1, we already knew this side was 2. So what is our side over here going to be? And again, we can do the work here. So I know that I have 1 squared plus, I'm going to call that b squared because it's a leg, and again this is what I'm looking for, is equal to 2 squared. Well, if I subtract the 1 squared to the other side, that gives me b squared is equal to 2 squared is 4, minus the 1 squared is 1. That's going to be 3. So b is equal to the square root of 3 right here. Okay. Well, again, it turns out if this length, okay, so now we're moving on to the more generic case. If your base is length s, that means your side across from the 90 degree angle is 2s. Now let me point out something more about the base too. The base is the side across from the 30 degree angle, the smallest side. So if you call that s, then the hypotenuse is always twice s, and the relationship of the other leg is s times the square root of 3. Remember, that's that square root of 3 that we got previously. These both, the 45, 45, 90 and the 30, 60, 90, are really worth memorizing those special cases of triangles because we use them so frequently. Now here's an example directly from the homework, and it's really going to be 2 examples. I've got example A here, and then I'll pull up an example B for you to try as well. So we're supposed to solve for the unknown, so I'm looking for both x and y. Now typically in the homework, when they ask you to find x and y, x might be the most reasonable to work on first, and in this case it definitely is. So when you're looking at this triangle, notice the overall triangle is a right triangle. And again, you note this from right there. That's a right triangle. So my hypotenuse is over here is x, which is the length of this entire side. So let's first use again, we've got a squared plus b squared is equal to c squared. I'm only allowed to use that if I have a right triangle, and I do, okay? Now, we're looking for the hypotenuse because that's across from the right angle. I'm not looking at y at all. I'm pretending like that y line is not even there for the moment. So one of my legs is 24 square root of 3. The other leg is 24. So here we go. So I'm going to say 24 square root of 3 squared plus 24 squared is equal to, instead of calling it c squared, I'm going to call it x squared because that's what it is. Now, when you square a product, okay, when you have a product raised to a power, we know those properties of exponents. I'm allowed to raise each one of those separately to that power. So I'm going to calculate 24 squared, and then I'm going to multiply that by the square root of 3 squared plus 24 squared equals x squared. Now I'm going to go to my calculator, and we know that 24 squared is equal to 576. What is the square root of 3 squared? Well, we know that square root and square are inverse properties of each other. So what happens here is these cancel, and I get 3. Okay, so that's going to be times 3. I meant to change that to, my bad, back to green. Okay, plus 24 squared is still 576, and that equals to x squared. Now we multiply first. Remember, order of operations, you multiply before you add. So 576 times 3 is 1,728 plus 576 is equal to x squared. And that gives me a total of 2,304 is equal to x squared. And then finally, I'm going to take the square root of that, and I get 48. So we found out that x is equal to 48. Okay, now let's see what we can do with y. Okay? And it may help to go ahead and label right here. I'm going to say x is equal to 48. Okay, now when you first look at y, okay, so now we're focused on the inside triangle, right? So right here, I'm looking at y. I'm trying to calculate that value. That's the altitude coming down. It meets at a right angle. Now, you might think you don't have enough information. We have the hypotenuse, right? 24 over here now is the hypotenuse of that right triangle. But we don't have this little green piece that I have highlighted here at the bottom. We know it's part of 48, but we don't know how much of a part of 48 it is. So let's go back and look at our big triangle. Let's look at relationships here. This is strategically placed in the lecture. Notice there's a relationship. We've got 24 and 48. How are they related? Well, 48 is twice 24. So this should make you reflect, hey, what if 24 is s, and then this side over here, that's our 2s, because that's 2 times 24. Oh, look, over here is s square root of 3. What does that mean? That's familiar, right? We just did this. So check it out. I'm going to go back to a familiar page. Here we go. So notice again, if you have a base, that's your s. That's our 24. That's across from the 30-degree angle. And then we know that the hypotenuse, of course, is the hypotenuse. And then the s square root of 3 is across from the 60-degree angle. Let's go back and plug in some degrees here, right? So that means that my s, that's 30 degrees right there because of the relationships of the sides. We know this, which means this is 60 degrees. We knew that top one was 90 degrees. That's nothing new. Now, how is that going to help me work with the next triangle? Okay, well, let me show you. So I'm going to label this triangle over here. Okay, there's my right angle. Okay, I know this is 60 degrees. I know this is 90. What does that mean? Well, that means that is 30 degrees. We know a lot now. Okay, now if this is 24, okay, remember how your hypotenuse relates to your 30-degree side? if you go back and look at the picture over here, okay, so the hypotenuse was 48 and our 30-degree side over here was half of that. So this is going to be 12, right? And then that means that y, you could use the Pythagorean theorem if you want to, or use that relationship. This is going to be 12 times the square root of 3. So we know that y is equal to 12 square root of 3. Now, not knowing those 30, 60, 90 relationships, we wouldn't have been able to pull this problem off, y'all. Now, here's part B. Notice it scooted over to the right because I just wanted us to have room to work on it. So notice the relationships here. They do tell us that this is 45, 45, and then 90. So this is a 45, 45, 90 triangle. Maybe we should go back and look at our 45, 45, 90 relationships. You want to? So when I go back, the special 45, 45, 90 triangle, notice that if side S and side S, then the hypotenuse is S square root of 2. Okay? So again, sides will be matching because you have matching base angles here. It's an isosceles triangle. And whatever S is, the hypotenuse is S square root of 2. So let's go back and look at our picture. Okay, so notice that we have 15 square root of 2. That's the hypotenuse here. Now you would argue that looking at the smaller triangle, this is also, I'm doing this in purple, this is also a 45, 45, 90, right? Has to be, because if this is 90, this is 45, that only leaves 45 there. You know what that means? That this is side 15, because the hypotenuse is 15 square root of 2, and y is 15. And we're supposed to answer the question, what is x and what is y? Okay, now y is definitely 15. What is x? Well, x is not 15, right? Because it goes all the way across. Therefore, x is actually 30. And we didn't do any calculation there other than knowing that this is a 45, 45, 90 relationship. Now, we could have found x without doing that, because we know if this is 15 square root of 2, and these have matching base angles, I'm looking at the big triangle now, okay, then this is also 15 square root of 2, okay. Actually, you still would have had to do it. I take that back because, oh, no, you wouldn't. I'm sorry. This is a right triangle. We could say 15 square root of 2 squared plus 15 square root of 2 squared is equal to x squared. We could have done that right off the bat. I promise you that's going to give you x is equal to 30. If you need to see the math right here, 15 squared is 225. The square root of 2 squared is 2. Plus 15 squared is 225. Square root of 2 squared is 2. Twice 225 is going to be 450, plus 450 is going to be 900, and you take the square root of 900, and that gives you that 30. But we just jumped in and used our special relationships right off the bat. Now there's a converse of the Pythagorean theorem. Do you remember what converse actually means? We talked about this in the logic section in your previous course in Math 231. Converse is when you state the theorem or whatever you're talking about the other way. I almost think about reverse when I think about converse. So this time for the Pythagorean theorem, it says if ABC is a triangle with sides of lengths A, B, and C, such that C squared equals A squared plus B squared, then triangle ABC is a right triangle. We typically use the Pythagorean theorem where we know we're dealing with a right triangle to start with, and then we calculate sides. But you know what? If you know the sides and they have this relationship, then you can prove that it's a right triangle. So that's the converse of the Pythagorean theorem. Now let's do an example or two before we call this video finished. And not the lecture finished, just part one of this video finished. Determine if the following can be lengths of the sides of a right triangle. Can this be a right triangle? In other words, let's use the converse of the Pythagorean theorem. So I know I have a side length of 51, 68, and 85. Now, which one might be the hypotenuse? Well, remember, it has to be the longer one. Okay, so the longer side has got to be the hypotenuse. So we're going to check if 51 squared plus 68 squared, does that really equal to 85 squared? That's all we have to do. So 51 squared is 2,601. plus 68 squared is 4,624. And 85 squared is 7,225. And then when you add these, I'm pretty sure it is by just looking at it, but I do want to verify completely. Sure, that's 7,225 equals 7,225. What does that really mean? Yes, this is a right triangle. How do we know? We used the Pythagorean theorem, and it held up. If it wasn't a right triangle, then this relationship wouldn't hold. Okay? And there's the typed up version for you, much more simplified. Try this one on your own. So here's B. I want you to pause it, try it out, just make sure you're comfortable with these steps. All right, what do you think? How did it go? First of all, what's the longest side? Well, we know square root of 13 has got to be bigger than both 2 and 3. That's the longer one. Why do we know that? Because, 3 squared is 9, right? So square root of 13 has to be bigger than 3. So we have 2 squared plus 3 squared. Does that really equal to the square root of 13 squared? Okay. There we go. So 2 squared we know is 4, 3 squared is 9, the square root of 13 squared. Remember, these are inverse operations of each other. They cancel out to give you 13. Look, 13 equals 13. Yes, yay, this is a right triangle. Let's do it one more time for a good measure. You want to? There's our quick work. One more time for a good measure. Pause it, then we'll shut this video down and come back for part 2. All right, how'd it go? Right, so again, 7 must be the one that might be the hypotenuse. Is that my C? It's the one you should try for C. So I have 3 squared plus 4 squared. Does that really equal to 7 squared? We know 3 plus 4 is 7, but 3 squared plus 4 squared, maybe not so much. 3 squared is 9. 4 squared is 16. 7 squared is 49. But 9 plus 16 is equal to 25, which is not equal to 49. So we know this is not a right triangle. All right. So let's shut this video down because I've gone over 32 minutes. Let's come back, talk more about the Pythagorean theorem, and then we'll talk about applications of the Pythagorean theorem, like the distance formula and the equation of a circle. I hope you have a good day. Let me know if you have any questions.